hosting this very interesting virtual conference and inviting me to give a talk. First of all, can you see my slide? Can you hear me?
Yep.
Everything. Okay, so we're good to go. So as you mentioned, I recently, actually, this year just started at Boston University, my independent research group. Of course, it's a very interesting year to get started with this endeavor. But in my research group here, we will look at functional structures over multiple length scales, particularly using self-assembly, including block-o-polymer self-assembly, as well as phase behavior and phase separation of complex fluids and polymers. And some of that I will touch on in my talk today. We're looking at structures out of functional materials, either responsive polymers as an example that you will hear today, but we're also very interested in inorganic solid state materials, in particular for energy storage, with a application range towards batteries. So this is kind of overall the research area we're interested in my group here. But today, of course, I will talk a little bit about the work I've done in the past to be able to show you a little bit of interesting data. And that is around the work I've done in the group of David Waits at Harvard, where I did my postdoc, using microfluidics to make interesting microcapsules with dynamic properties. And here's a couple of videos that I hope makes you interested in staying online and listening to my talk, and we'll get to what they show. Now, talking about microcapsules, I want to point out first, very importantly, that we're now probably talking about somewhat of a different length scale than what we've heard a lot today and yesterday. We're truly talking about particles that are on the order of at least a few microns, typically tens of microns to hundreds of microns in diameter. But these capsules and particles on those length scales are used, of course, quite widely to encapsulate sensitive materials, to protect them during their shelf life, and then to provide a controlled release mechanism to release the active ingredients at the point where they're needed. We find these in every application. One of the real big applications for microcapsules in particular that I understand in industry is really the detergent industry and the fragrance industry, particularly in laundry detergent, to make sure that the interesting smells that you get when you wash your laundry are only released, those fragrances, inside your washing machine. And it uses a very simple trigger mechanism of somewhat brittle capsules that break in the machine when they start being agitated and release the fragrances. Very big market there for that. Now, in terms of particles versus capsules, of course, you know that in solid particles, including active ingredients, we intimately mix our active ingredients with our encapsulation material, which may be of advantage, but can be of disadvantage, especially if we think about some of the biologics that are often very, very sensitive to any kind of chemistry, polymer chemistry, monomers that we try to expose them to. Now, microcapsules have the advantage that they can be loaded with a liquid cargo core. So whatever your cargo is, if it's liquid itself or dissolved in a liquid solution or in a dispersion, it is independent of your encapsulation material. The encapsulation material purely forms the shell and is therefore separated from your interior material and acts truly just as the gatekeeper to both protect the interior as well as decide when to release the active ingredient on what kind of trigger or what kind of pace. At the same time, the amount of encapsulant, especially when you talk of the tens to hundreds of micrometer scale, the amount of material that encapsulates your active ingredient in the core can be very, very small compared to the amount of cargo that you can put in it. You can imagine a shell of a micrometer thickness gives you quite a bit of protection at a particle size of 100 micrometers. That is probably less than 10 weight% of that capsule. Now, what we typically see for capsules is either we get some kind of diffusive release, which we see in solid particles as well, or we can have a burst release, which truly just depends on the breakage of the shell, which allows all the ingredients to be released at once. And both of these events can, depending on the chemistry of the shell, be dialed in to have a certain time delay or rate at which they happen. Now, there's different methods of making these core shell microcapsules, particularly with liquid cargo cores. The method of choice that we like to use is that of complex emulsions, where we use these core shell double emulsions. Here I show a water core surrounded by an oil shell, what we call a double emulsion, which is dispersed in an outer fluid, often water again, and the shell and the oil shell separates the two water phases. And upon solidification of the shell, we obtain our microcapsules with different triggers. There's other ways to make microcapsules. One that's pursued in industry quite a bit is simply interfacial reactions between, for example, a water drop containing monomer A and an oil continuous phase with monomer B. We all know the good old nylon experiment where you form polymers at the interface between oil and water with the respective monomers present. Now, a bulk way of making emulsions, of course, is homogenization or high shear emulsification, just simply mixing water with oil to get what we call here these water and oil emulsions. But for complex drops that I discussed, such as double emulsions, one would need to take these pre-emulsions and emulsify them a second time. That's how it is typically done to obtain these water cores inside oil shells. And of course, there can be quite a bit of heterogeneity using that, even though with homogenization and extrusion, people have become pretty good in getting the dispersity of even such complex emulsion drops fairly far low. But if you're interested in tuning and understanding particularly the architectural features of your microcapsules, a good method of choice that we like to use is microfluidic emulsification, where we control the architecture of these microdroplets very precisely by simply controlling the flow rate. So here's a video of nested glass capillaries, what you see here, where you have three fluids flowing, one fluid that comes in from this barely visible interior capillary here, a water core, for example. You have this umbrella here of oil that encapsulate that water drop that comes in from the left side. And then you have more water coming from the outside, and all of these fluids going through this junction here form these double emulsion drops that have a water core and an oil phase, and an oil shell dispersed in water. You can see that they're very homogeneous. You can control the size to a certain extent using the flow rates and the geometry of your device. The other very interesting thing, apart from the structural features, is of course that you have a quantitative encapsulation efficiency here. Unless, of course, your flow breaks up, you have every interior water phase encapsulated in oil, which in bulk homogenization or bulk emulsification is often not the case. And if you think about biologics, which makes it interesting even for somewhat scaled up production of these drops and capsules, the shear rates that the liquids are exposed to in these microfluidics is often much lower than what you find in high shear processes in bulk emulsification. All right. Maybe it lets me. There we go. So now the question is, what happens if we, or how do we solidify our double emulsion shells to get microcapsules? Two common ways I want to mention here. One is using monomers as the oil shell or part of the oil shell that you can simply, upon a UV or heat trigger, polymerize to make a solid cross-linked shell. The other option, of course, is to use a solution, a hydrophobic solution, if we have water, oil, water, double emulsions, of a polymer where the solvent that the polymer is dissolved in then simply evaporates, even though it is an emulsion, so it actually diffuses through the outer phase and then evaporates from the outer water phase into the atmosphere. But we still call it somewhat an evaporation process to form polymer shells. Today, I will touch on two stories. One of each one will deal with polymerization, solidification of double emulsions, and the other one with pre-made polymers that are solidified through evaporation. There's a couple other methods to make solid shells out of double emulsions, such as freezing of a shell material from above to below its melting point, but these are the most common techniques that are used. Now, I've shown this picture early on, really what has been done in the microfluidics community over the last 10, 15 years or so, and of course, beyond that in emulsification for many decades, is making these capsule architectures with various triggers that allow you to trigger the event upon which your cargo is released. Here, the video just shows a polystyrene microcapsule that's filled with these small colloids that upon triggering here, meeting a oil phase, in fact, that interfaces the water phase, releases its cargo. But of course, all these mechanisms that we have seen over the decades are destructive. The microcapsules are truly a one-way encapsulant. You encapsulate, they release, and they're typically done with their job and hopefully degrade, but often accumulate. Now, a new concept, or an interesting concept we were interested in applying to microcapsules, is using reversible triggers of our permeability or other properties of our microcapsules. In the simplest case, can we turn our microcapsule repeatedly on and off to permeate or let cargo diffuse through the shell? If we were able to do that, of course, we could have a more complex release profiles that allows us to actively stop and start the release from the capsule, or allow the capsule to release on demand due to the changing environment. And it would also allow us for microcapsules to do something fairly unheard of, is to actually load the capsules after their fabrication, trap whatever we loaded inside the capsules, and release again through a different trigger. Of course, these are things that are well known in particles, and hydrogels we've heard quite a bit about in this symposium or conference are a fantastic material for that. You can trigger them through temperature, through pH, even through light these days to change their mesh size or change their swelling behavior in water. And that works really well in micro particles. However, capsules, there's very little been done around using these trigger responsive hydrogels or other trigger responsive materials as shell-around capsules. Particularly if we're interested in having water cored capsules, it is kind of tricky to use these emulsion ideas to form a hydrogel shell around our water drops because of the simple miscibility issue of many hydrogel monomers or polymers with water. So emulsification can be an issue. So that was really one of the points we wanted to address to get, in this case, pH responsive hydrogels. Now, one of the ways from a molecular design standpoint that we found works very well to make pH responsive hydrogels is to use reactive anhydrides as monomers that then, as you all know, upon hydrolysis in water simply form carboxylic acids. And carboxylic acids are, of course, the functional group for pH responsive polymers or hydrogels that swell at pHs above their pKa and that usually shrink or turn more hydrophobic at pHs below their pKa. So our strategy here was to use these hydrophobic, water immiscible anhydride monomers and crosslinkers to form a polyanhydride network that we then, without harsh chemical treatment, simply by leaving them in their native water environment, hydrolyze towards polyacid networks in the shell that are done pH responsive. Now, we did this with a couple of systems. The one that I really like and would like to present to you is what I call the thiolene system, where we use these in this case, a thiol crosslinker with 4 thiol functional groups, as well as dienes, a permanently cross-linking diene, this triethylene glycol divinyl ether here, as well as the pentanoic anhydride, which has also 2 vinyl groups at the end, and our anhydride group in the middle, which can hydrolyze. All these monomers are water immiscible and can serve as the oil shell of our double emulsions. And upon simple UV triggering of the thiolene chemistry, we obtain very homogeneous shells of these polyanhydride cross-link networks, which is still highly hydrophobic. And over time, this anhydride hydrolyzes and the shell turns into a polymer network that has tethered carboxylic acid groups on it, which make it pH responsive because they get charged upon increase of the pH. We also looked at a system which uses kind of the standard acrylate or methacrylate chemistry using methacrylic anhydride. That also works very well. I'm not going to talk about it today, but if you're interested in that, it was published in this macromolecules paper down here. Now, a little more about these devices, because a lot of you might not have seen these before. One way to make microfluidic drop makers is simply using glass capillaries. And on the bottom right here, I show a picture of them, and that is truly how simple they are. You use glass capillaries that are tapered on one side, and you can control the size of this taper, which has an influence on your particle size. And you nest them inside typically a square capillary, or if you can also coaxially insert them into another round capillary. And you see here in the middle, there's the junction between the two tips of the capillaries that have an outlet back here and an inlet through these glued on needles. And then you also flow liquids through the square capillary. And those are your phases. And you can, of course, nest as many capillaries as you want if you are interested in getting more and more phases or liquids that form different orders of shells. Now, here's an example of making these microcapsules. It's fairly thin shell. You can see here, this looks like a simple drop, but believe me, there's a thin shell of oil encapsulating a water drop. Here, it's a little clearer where we make a thicker shell. And again, the architectural features are purely dependent on the architecture of the size of your microfluidic junction, as well as the flow rates of your water and oil phases. Now, here's a few micrographs on the top, just optical micrographs of microcapsules that we've done at different geometries, from very thin shells. Here, these are so thin they actually buckle slightly under the osmotic imbalance between the interior water phase and the exterior water phase, to microcapsules that are fairly thick. On the bottom are the corresponding SEM images, where you see here a cross-section of the microcapsules. So these shells are typically as thin as a couple micrometers for these systems, and we can make them up to tens of micrometers. An important note here is that if the density, of course, of your core liquid and your shell liquid is not balanced, you will get this asymmetric positioning of your core within your shell, which is, of course, more extremely visible in the thicker shells, which you have to account for if you think about release profiles or diffusion through your shell, that your shell is usually not of homogeneous thickness, especially if they're thicker. And the very thin shells, you typically see a fairly homogeneous thickness within our measurements. Now, another way, and maybe a little more elegant, to make microfluidic drops is using PDMS devices. Here you see just a photograph of one of these devices that are obtained from soft lithography, where we stamp our channels into PDMS and then cure it. And here on the left side, you see a video of making these, where we have now two junctions. At the first junction, where our inner phase water meets our shell phase, the oil, and then those two phases get coaxially encapsulated into another outer phase oil to form our complex emulsion drops. The nice thing with using lithography defined devices here is, of course, that you have great control over the size and length scale of your channels, and therefore good control over the length scale of your emulsion drops and microcapsules. And it allows you to get to smaller length scales, even down to single micrometers, if you go from PDMS to silicon lithography. Now, the first step, of course, in our chemistry was to look at the hydrolysis of our polyanhydride shells towards polyacid capsules. We looked by IR and found that after some time, we see this increase in broad peak and high wave numbers here, which is indicative of OH groups, as well as the decrease of this very faint peak that you might be able to see here that's typical for the anhydride unit. More macroscopically, we can, of course, look at an encapsulated probe molecule here, sulforhodamine B, which does not diffuse through the hydrophobic shell that is the anhydride initially. But over time, we see that when the shell hydrolyzes to a polyacid network, the hydrophilic sulforhodamine B can diffuse out of that shell. And you also see, of course, an increase in the size of our microcapsule due to the swelling of the shell now with water after it turns into a more hydrophilic polymer shell. And that increase and change of hydrophilicity is something that we were very interested in this thiolene system, because as you remember, the thiolene system, even in its state where it is already hydrolyzed, the amount of hydrophobic components here in this network is very high. So if there's no charge at low pH where these carboxylic acids are protonated, the overall network hydrophilicity is very low. It's still a very hydrophobic network, and not much water actually swells it. Only when we charge these groups at higher pHs do we see a significant swelling. And this is what you see here. Here is going to be a video where we switch the pH from 4 to 9.5, and you can see what happens to these capsules. Now they undergo this very interesting phase transformation or shape transformation, because one thing that is unique, of course, about capsules compared to particles, only the shell is the actual responsive part. The interior core is totally ambivalent to what happens to the pH and has no interest in swelling whatsoever. Therefore, in the beginning of the swelling process, when the shell extends in volume and surface area, it starts buckling because the interior volume does not change as quickly until the water has managed to diffuse in and we get our increased spherical microcapsules. Now, if we turn this whole thing around and now take these microcapsules and see if we can shrink them back down to their low pH behavior, what we found with these microcapsules is that in fact takes very long. They can swell to their final size within easily 15 minutes or so, and that's only due to the buckling and then the increase due to water diffusion. But their decrease in size actually takes almost a day for these particular microcapsules. And the reason for that is that the shell, once we turn the pH to lower values than its pKa, immediately turns so hydrophobic that the water diffusion out of the capsule, which needs to happen in order for the capsule to shrink, is slowed down significantly. And you can see that that water pressure, or the pressure that the shell exerts on that water core, is actually visible in really these deformation of the shell. But interestingly, the microcapsule structural integrity is still provided, and we attribute that to the very homogeneous network that thiolene chemistry can provide you with, and a very low defect rate of these networks. Now, you can include various amounts of anhydrates in your initial monomer mixture, which then will give you various different compositions of polyacid to permanent crosslinker. So different crosslinking densities lead, of course, to differently well-pronounced increases in size, meaning swelling of the shell for these capsules. Now, the swelling of the shell and the pH responsive size change of these capsules, of course, is one thing, but we were interested in how that impacts permeability. So here you see these medium cross-linked shells at pH 4, where they're impermeable to a 4.4 kilodalton fluorescent probe. Dextran is the probe we're using here. Now, if we increase the pH, the same capsules now at pH 9.5 are permeable to molecules at least up to 10 kilodalton. Again, dextran, fluorescently labeled dextran molecules. And at 20 kilodalton is around our cutoff for these capsules, where we see some heterogeneity throughout the capsules, but anything bigger than that is blocked even at the high pH, which also shows you that these capsules don't break during their shape change. Now, here's capsules that had a lower cross-link density. With the lower cross-link density at low pH, anything bigger than 20 kilodalton was blocked still at that stage. But when we increased the pH, in this case to 11, but even at 9.5, it was the same, we were able to diffuse 70 kilodalton macromolecules through the shell, while much larger molecules were still blocked. So there's quite a dynamic range that we can dial into these capsules by their cross-link density. And then once we have the capsules made, there's quite a range that we can span by triggering, in this case, with pH. Now, how fast does that change is, of course, of interest if we think about capturing, trapping, or releasing molecules. So here's will be a video, fluorescent video, that is taking over 3 minutes, where we take capsules that are not filled with a 4.4 kilodalton fluorescently labeled dextran, and we switch the pH from 4.5 to 9.5. And you can see that the fusion happens within the first minute, and the filling of these capsules, fairly thin shelled in this case, is done within a couple of minutes. Now, is that process reversible? Can we take these capsules now and turn back the pH to low pHs to trap the molecules we just captured in our capsules? Or is there some kind of latent time where the cargo can diffuse out before our capsules actually turn their permeability off. And for this Sialine system, we found that within a couple seconds of changing the pH, the shell turns so impermeable and so hydrophobic that our probe molecule is permanently trapped on the inside. Now, this, of course, allows us to have this truly on-off or on-demand kind of release profile where we simply can change back and forth the pH of capsules that are loaded with a probe molecule. Here, a slightly larger probe molecule to prevent too fast diffusion out of the capsules. But we can stop the release of those molecules for quite some time and then turn it on for short pulses that we're interested in and do that over numerous cycles. So we truly achieved for microcapsules now what's been achieved for a long time in microparticles with this dynamic on-off response or reversible on-off response. Now, you can use polyacids, of course, also with other triggers. So these are responsive to divalent ions such as calcium as well. So instead of pH, you can, at the deprotonated state, use calcium to trap molecules. And then, for example, EDTA, which removes the calcium from our polyacid network shell to trigger the release profile. So even with the same system, we have a couple of different release mechanisms that we can think about. Now, the second story will be a little faster, just a couple slides on this, was an idea that I brought from my PhD, where I worked a lot with mesoporous materials, is can we make microcapsules with shells that have nanopores, and in particular that have nanopores that are stimuli responsive, like we have in some of the stimuli responsive water filtration membranes, where we can turn these nanopores on and off for permeability of larger molecules. And of course, blockopolymers is a great way of making nanostructured materials and even nanoporous materials. For those of you who don't know, quick introduction of blockopolymers. We've seen quite a bit of it today. What I'm interested in blockopolymers is actually their solid state self-assembly, which happens somewhat different than their solution self-assembly of micelles, where in blockopolymers that have equal ratios, for example, of the two blocks here, they typically form these lamellae sheets in the solid state. And depending on the block ratios or volume fractions of them, they can form these micellar packed assemblies or these cylinders or even these three-dimensional gyroid structures. And if you turn the curvature around by making the red block bigger, of course, you get the inverse structures of those. So these are commonly observed solid state structures that blockopolymers self-assemble into, depending on the volume fraction of, for example, polystyrene and poly-4-vinylpyridine, a hydrophobic and hydrophilic polymer. Now, you can introduce porosity into these non-porous solid state assemblies by adding sacrificial porogens. And this is a system that's been studied quite a bit by Professor Ikola in Helsinki and Tim Brinke in the Netherlands and others, where they use these polystyrene 4-vinylpyridine blockopolymers together with these aliphatic phenols that can be rinsed out after self-assembly to form a porous blockopolymer structure. And with the 4-vinylpyridine being, of course, pH responsive, you can make these pores, or these pores are rendered pH responsive as well and close upon acidification of the surrounding environment. Now, we chose in this case to use these polymers and porogens in hydrophobic solvents and made our double emulsions again to obtain double emulsions with our blockopolymers. And then upon evaporation or diffusion of the solvent from the shell, we get solidified shells. Now, first, when we looked at the diblock copolymer with our porogen that formed a cylindrical nanostructure, we were interested, will these cylinders align around the shell parallel to the surface of the shell or perpendicular? And of course, as is often seen in blockopolymer self-assembly, one of these blocks prefers the interface to the water, and we found cylinders that form that parallel to the shell surface, and with that are fairly useless if we want permeation throughout our shell that we can control transport in and out of our microcapsules. Therefore, we focused on triblock terpolymers, in this case, a polyisoprene polystyrene 4-vinylpyridine, which are known to have much larger phase windows of these three-dimensionally connected or bicontinuous structures. In this case, the gyroidal structure under the compositions given here, we were able to form this gyroidal structure in the bulk, and that makes the need of aligning the porosity to the surface unnecessary, since this is a three-dimensionally connected porous network. The other advantage of using this particular polymer is that we can use the double bonds and some polyfunctional thiols to cross-link these shells after self-assembly to provide them with a little more mechanical robustness, which is often a problem if you make non-cross-linked polymer microcapsules using the solvent evaporation approach. Here we can, after self-assembly, cross-link these systems and therefore are less susceptible to mechanical failure. So here, in fact, we're able to take our triblocopolymer microcapsules and put them even from water into methanol without any breakage of these capsules. And when we made capsules of various thicknesses, we saw that for very thin shells here of a few hundred nanometers, we get this very disordered porous network, which is not unsurprising. Thin films of blocopolymers typically don't self-assemble well due to the fast evaporation of the solvent, but thicker films here self-assemble in very beautiful gyroid network morphologies in these tubular networks that you see here. Now the question is, of course, are these homogeneously responsive to pH? We expected that at low pH, due to the protonation of the 4-vinyl pyridine, the pores will be closed, which has been found in flat water treatment membranes before. And at pH above the pKa of 4.5, we will have open pores. Now we found, first of all, that the capsules are impermeable at any pH to large 100 nanometers fluorescently labeled polystyrene nanoparticles. So that's good. There are no large defects in our microcapsules. However, when we looked at high pH using a smaller molecular probe here, 250 kilodalton dextrin again, we found that a lot of the capsules were permeable to this probe. However, a few capsules did not allow permeation of this probe. When we lowered to pH, we found that more capsules, as expected, were not permeable to our probe. However, there were still some capsules, in fact, quite a lot of capsules, over 45% of the ones we counted, that were still permeable to the probe. So that puzzled us a little bit, and why there is such a heterogeneous permeability in microcapsules that have such homogeneous cross-sectional structure that I showed you before. One thing that we found is that it is not just about the cross-sectional structure and the porosity throughout the shell. Very important, of course, is the porosity that is on top of the shell, or the inside and outside of the shell surface. And we found there that while some capsules displayed similar porosity on the surface as in the cross-section, other capsules showed somewhat different, lower fraction of porosity or no porosity at all. Of course, we couldn't look at every capsule all the way around in SEM, but we assume that there's quite a bit of heterogeneity in these capsules, even though they're all made through this continuous same process of microfluidic templating in these systems, and that there are quite a few capsules that have this capping layer, which is known from thin film solid polymer self-assembly at the water-oil interface, and therefore block diffusion into these capsules at any interior. So this is something that it still needs to be addressed to be able to allow these to be 100% functional or homogeneous. But this is where I will end my talk, with just a brief curiosity that we found and that we thought was very interesting for hierarchical materials. You might have not seen it earlier, but the aqueous phase that we used to contain quite a lot of salt. The salinity, we had 1 molar of potassium chloride. And the reason for that was that when we used no salt in our solutions, what we found is that our capsules during the evaporation process turned very heterogeneous optically. And in the SEM image, we found these large voids inside the shell. Between the voids, we had our blockopolymer self-assembly. And we hypothesized that that is due to emulsification, self-emulsification of water into the oil shell due to the amphiphilic blockopolymer that then leads to water drops that phase separate within the shell, which has been seen in single emulsion oil drops just a few years ago as well. And therefore, in our capsule shell, we formed these micron-sized pores together with our nano-sized pores. However, these pores did not cause the capsules to break, very interestingly, even though these ones were not including the cross-linking chemistry, the thiolene chemistry I described before. So it's a very interesting way potentially of making hierarchically porous shells for these systems. With that, I want to wrap up and thank in particular the students that were involved in this work. The hydrogel work was done together with Saraf Nawar, who last year graduated. out of David Waite's groups, as well as Brenton Devaney, a PhD student in the group. And Jung Wu worked with, on some of these hydrogel systems with other triggers that I did not show today. And Yo-Min Lee was a professor at Postec in Korea, worked with me on some of the polymers. And I have to thank my PhD advisor, whose lab I used to make the blockopolymers that I showed here today. And I will just leave you with some videos and pictures. And thank you very much for your attention. I'm happy to answer questions you might have.